Question 9 from assignment related to astrophysics and cosmology. A series of observations are made by a nearby stars over a number of years. The stars are seen to undergo very small oscillatory motion, appear to wobble against the background or a more distant star. Describe how astronomers use this wobble to calculate the distance of a nearby star. What actually we do, to work out the distance between us and the nearby star. So we view the star like say these are the background stars, because according to trigonometric parallax, this is a trigonometric parallax. According to that, if two objects are moving away from two objects are moving, the object which is closer to us will appear to move at a higher speed as compared to object far from us, even though two objects moving with the same speed, but it will appear that this object cover a greater distance relatively as compared to object which is far. So what we do, we have the background stars, like stars which are far from us, so their relative change in position is negligible or very small. So we focus on, and this technique can be used for nearby star. Like example, so we focus on any one of the nearby star and we observe for a duration or for a period of a 6 month. So what we actually do, like example, this is the sun and we are observing from the earth. The distance between the earth and the sun, that is known as the 1 astronomical unit. One, that is also the radius of the orbit, which is equivalent to 1 astronomical unit. So what we do, like this astronomical unit is known, like we know this is like and we observe this star for a duration of a 6 month. Like earth is here, after 6 months this distance is known and we are observing the star. Say star is somewhat here. In exam, you can also draw, like you can also obtain full marks for trigonometric parallax if you draw it correctly. So what we actually do, like we have these, even if you draw, like we don't write anything for, especially for trigonometric parallax, and you draw it correctly, all the labels and drawing is clear, you will score all the full mark. So you can obtain full marks by annotated diagram as well. So say we are focusing on this star. So we observe this star with reference to, like we make our origin, so let's say with reference to this. And this angle, example, say we say theta 1, like with reference to background, what is the angle here? We call that as a theta 1. Now, after a 6 month, the position of Earth will change. Say after 6 months, we are here. And the motion is not in this manner, like motion is around it in this way. Like in this manner, motion in this axis, vertical axis. If I'm saying Earth is in a vertical axis to explain the idea. Otherwise, if I draw horizontally, you may find it difficult. So it's moving in a vertical axis. So after 6 month duration, the Earth will be here. And again, we observe the same star for after a 6 month duration. With reference to the background star. So this is theta 2. So we have the angles and the distance between, like, this is star, what we are referring, like we are referring what will the distance of the star with reference to the sun. So example, the distance between, first thing we have to identify, like making a right angle, a simple diagram, this is like what is actually what we do. But if you want to understand in simple way, like first this is a sun, we observe, we are here, we observe the star, and after when we observe this star, this is one astronomical unit, this distance is d. We observe this star, so we call this angle as theta. And after a 6 month duration, we again observe this. This is as one astronomical unit, this d. So this angle is also theta. So like we'll have basically two theta. So to get theta, because why we are observing for a duration of a 6 month, otherwise if we only observe at a specific point, it will be very small value. So we observe for a duration of a 6 months. So this total angle, if I say phi, in a duration of a 6 months, this is phi. So if I need theta for half of it, so phi divided by 2, I will get theta. So we have, like if we need d, the distance, and we have this radius, and we have the angle. So what we can work out, like we can work out the distance between the star and the sun. Like this distance is there, the relative distance between the star and the sun. Or if we have the angle and the radius, we can also work out this hypotenuse as well. So this is how a trigonometric parallax work. So what we do, we view the star from two different positions at 6 months interval. And then the change in angle position of a star against the background, we measure, and using a trigonometry, we calculated the distance to the star, and the diameter or the radius of the Earth orbit is known, which is one astronomical unit. Is it clear how a trigonometric parallax work? In question 10, in 20th century, the Edwin Hubble analyzed the light from a distant cluster of galaxies and deduced that these clusters are receding. Explain how Hubble was able to deduce the distance cluster galaxies are receding. So what he did, he actually observed the light from the galaxies to be to show a redshift. And using redshift means, like due to Doppler effect or a redshift, so most of the galaxies were giving a redshift. Redshift means like the wavelength which we observe was increasing. If a wavelength is increasing, it means they are moving away from us. If it was a blue shift, then it means it is moving closer to us. The table shows some Hubble's original data on the distance to some cluster of galaxies and speed which the clusters are receding. You can see the galaxies which are closer to us are moving slower, but the galaxies which are far from us are moving faster, as the speed in 10 exponent 5 is there. Another cluster is there. Pegasus was calculated to have a distance from 2.2 exponent 23 and to be recede at a speed of 39. So it was 2.2 and 39. Comment on these values in relation to a data provided in the table. So what you conclude from this, you can say the distance is similar to that of Pisces, as you can see, like 2.2 and 2.3. So however, the speed is slightly smaller. Like this Pegasus will be here and the speed is 39. So, and what is the relation here? As the distance is increasing, the speed, recession speed is also increasing. Then cluster is there too far from Earth for a parallax to be used. Determine how a distance from the Earth and how the distance could be determined. How we can determine distance of the stars or galaxies which are far from us. We cannot use trigonometric parallax. So first what we determine the redshift. Like or they already mentioned. So what else we can consider? We can also consider them as a standard candle. If you use a standard candle, what happened in a standard candle, we consider that the stellar object is having a known luminosity. Like we know its power and how much flux we receive on the earth. So we compare that the flux is equals to the luminosity divided by 4 pi d square, where d is a distance. So if we need the distance, d is equals to L, d square is equals to L divided by 4 pi into flux. Or if we take a root, so d is equals to under root L divided by 4 pi flux. So what we do, like we'll consider it has a known, we'll use a standard candle. And if we say a standard candle, it means the object which is emitting out the light having a known luminosity. We know its luminosity or the power. And we measure the flux. Flux can be measured. Flux means how much light enter on a unit area, that is called a flux. So we measure the flux and we use the inverse square law. Like if a flux is, if the distance is double, the flux will be decreased by 4. If distance is p times, the flux will decrease by 9. So using that, we work out its distance using this formula. So one mark mentioning standard candle. What is standard candle? We'll consider that it has a known luminosity. From its known luminosity, we work out the distance. We measure the flux. Flux can be measured, and then we work out the distance. Hubble's data has been used to plot a graph, speed and distance. Use a graph show that the Hubble data suggests that the age of a universe is 5 into 10 to the power minus 16. So what you have to do, the slope of the, you have to work out the gradient, which will be y2 minus y1 over x2 minus x1. The gradient will be equals to the Hubble's law, Hubble's constant. And reciprocal of the Hubble constant is the age of the universe. So first take any 2 points on this line, find the gradient. And don't forget to substitute the unit correctly, like this is 10 power 5. So when you take any point, it should include 10 power 5 with that. And here this is 10 power 23, include that as well. So this will, you will take a gradient, you get the Hubble constant and take a reciprocal, you'll get the age of the universe from the graph. The current acceptable value of the age of a universe is 4.3 exponent 17. Suggest why Hubble original data leads to value almost 10 times smaller. Why? The main reason, the current accepted value, you can see it's 10 power 4.3 exponent 17 second. And why the Hubble's original data leads to a value almost 10 times smaller? Because this data, we did not plot for the galaxies which are too far from us. Like in this, like few galaxies are plotted here in this original data. So few galaxies are there, so there is a higher uncertainty in value of Hubble constant. That's why the value appeared to be much higher than the current value. And Hubble's law is generally accepted as an indication that the universe is expanding. However, the idea of a universe has been challenged by some scientists. These scientists suggest that the mass of electron in an atom increases over a time, causes a photon emitted by an atom to be more energetic. Use this suggestion to explain, the scientists might conclude the universe is not expanding. So as electrons are moving, the mass of electron is increasing, so they release different photons when they transit between the shell. As they transit between the shell, the photon which will emit out will be different. So with reference to that, like use this to explain how scientists might conclude that the universe is not expanding. So how they can conclude that, how we conclude universe is expanding, because the wavelength which we receive, that is having a shorter wavelength. So means we say that the objects are moving away from each, but the photon would be, So the idea is that because if atom like electron mass is increasing, it is producing a photon of high energy. If it is producing a photon of high energy, high frequency and shorter wavelength. But in the past, the electron, when it was not increasing, like from a distant galaxies, this electron which was lighter, when this was emitting out a photon, it was having a lighter, so smaller energy, smaller frequency, or a longer wavelength. So means in the past, those photons which we are receiving right now, like the galaxies which are distant galaxy and emitting out those photon, those galaxies were emitting out longer wavelengths. As a result, what we say that universe is expanding. Like the galaxies which are far from us, or the distant galaxies, the photon which we receive from them now, that photon is having a longer wavelength. So that what might be a reason that electrons, as we say, the electrons were lighter. Like now electrons are getting heavy, but electrons were lighter in the past. So these electrons were emitting out a smaller energy or a longer wavelength. That's why this might not be true. Because what we assume the photon which is emitted out by the electron now and the past were same. But now it is found that some of the electrons are increasing in mass, so it is emitting out high energy photon or a shorter wavelength. So what might happen according to current situation, that maybe the photons which are coming out from those galaxies might be emitted out from electron which are lighter, so they emit out longer wavelength. Instead of the galaxy move away from us, the longer wavelength might be due to the lighter electron rather than the movement of the galaxy.